Hi class, Matt here. I wanted to do a follow-up lecture to section 10.1 on section 10.2. Section 10.1 was all just about parametric equations. This one is going to be bringing some of the calculus to it. So I'm going to go through the slides here for this lecture, and it's going to cover four main topics: um, tangent lines, areas, arc length, and surface area. Now, I'm not going to spend too much time focusing on the algebra and calculus in this video. That's just because from Calc 1 or Calc 2, you should remember a lot of it. Um, but this whole section is just going to talk about calculus parametric curves, and it's actually pretty easy. It's just the calculus that you've learned. A lot of it is Calc 1, just relating it to parametric equations. It's actually really straightforward. So why don't we start with the easy stuff here? All right, so this is tangents or specifically tangent lines. Okay. So suppose you have two functions, f and g, they're differentiable functions. And we want to find the tangent line at the point on a parametric curve. So x is a function of that third variable t, and y is also a function of that third variable t. All right, and this, what we're saying here is y is also a differentiable function of x. So if we have the chain rule, if we want to find dy dt, well, you take the derivative of y with respect to x, but then remember x is defined by a third variable t, so then you must multiply that by dx dt. Now what we ultimately want to find is dy dx. So if you get dy dx by itself, you're just going to divide dx dt over, and that's what you're going to get. So whenever you have parametric equations, dy dx is just equal to dy dt divided by dx dt. Right? Just recall, obviously, dx dt can't equal 0 because you can never divide by 0. All right, so equation 1, this first one here, enables us to find the slope of dy dx of the tangent to the parametric curve without, like we saw in the previous section, having to eliminate the parameter t. All right, so what we can see also too, when I talk about horizontal and vertical tangent lines, you have a horizontal tangent line when dy dt equals 0. So when the top dy dt equals 0, obviously when you have slope 0, that's a horizontal tangent line. And there's a vertical tangent line when dx dt equals 0, or when the bottom here equals 0. Obviously, whenever you divide by 0 here, you can't have it, so you're going to have that vertical tangent line. All right, that's obviously remember from Calc 1. All right, this information is useful for sketching parametric curves. We'll see that later on. All right, it's also useful to consider the second derivative. Remember what the second derivative did in calculus here? In Calc 1, the second derivative was used to find concavity. So all you're going to do is differentiate with respect to x, this dy dx that you just found, which is this equation right here. So you're going to differentiate this again. So all you're going to do is you're going to take the derivative with respect to t at the top and divide that by dx dt. All right, so let me walk you through a quick example. So you have this curve C is defined by the parametric equations x is equal to t squared and y is equal to t cubed minus 3t. So you have these two things. You have x is equal to t squared, y is t3 or t to the third power minus 3t. Four questions here. Show that C has two tangents at the point 3, 0, okay, and find their equations. All right, from that, find the points on C where the tangent is horizontal and vertical. Great. Determine where the curve is concave upward or concave downward. No problem. And then let's sketch the curve. All right, so let's do the first one here. Show that it has two tangents at the point 3, 0 and find their equations. So if you take the two equations, let's just start with y, okay, because what we're saying here is y is equal to 0, all right? And you solve, you set it equal to 0 and solve, you'll get the following answers. You'll get 1 here, just factoring out a t. T is equal to 0, or t is equal to plus and minus the square root of 3. All right, but if you look back here, if you plug t in for 0 in here, you would get 0 squared. You get x is equal to 0, so you can't have that one, all right? But the other two are plus and minus the square root of 3. So this point here, 3, 0 on C arises from two values of the parameter. T is equal to square root of 3 and t is equal to negative the square root of 3. So because the same point, okay, and remember 0, you can't have 0. Let me go back because if you plug 0 in here, you get x is equal to 0. It doesn't work. But because this point has remember it's 1 point, but 2 t-values get there, that means it's going to cross there. Okay, so when 2 t-values get you the same point, that means the graph crosses. All right, so this indicates that it crosses itself here. And remember what we're trying to do here. All right, show that it has 2 tangent points. All right. If I look at the derivative here, all right, now I'm going into the second part here, horizontal and vertical tangents. All right, since the derivative, if you take dy dt, the derivative of y with respect to t is this, derivative of x with respect to t is this. All right, you can simply factor out 3/2 here, make it look nice. Right, the slope of the tangent line when t is equal to plus or minus 3, if you were to plug this in here, I'm just going to save the algebra. All right, I'm going to plug this in here. All right, dy dx becomes plus or minus 6 over 2 square roots of 3, which is equal to plus or minus the square root of 3. So I apologize. I said we're moving on to b, but sorry, I'm skipping around here a little. All right, 2 tangent lines, and find their equations. So what I did here was I found the derivative. Remember, derivative gives us the slope of the tangent line. So I plugged in t is equal to plus or minus the square root of 3, and I got 2 different slopes. All right, so one is plus the square root of 3, one is minus the square root of 3. So the equations of the tangents at the point 3, 0, I'm just using the point slope formula, is y minus 0, so I'm just leaving that, times slope times x minus the x value 3. And it's the same thing here with negative square root of 3. All right, so I showed by showing that the same t-value got the same point, or 2 different t-values got the same point, I know that they crossed. I found the derivative, plugged the t-value in, and use that to find the slope, and then use that to find the equations. All right, B. Let's look to see where C has a horizontal, or find a horizontal and vertical tangent line. So C, the curve C has a horizontal tangent line when the top, dy dx is equal to 0. That is when dy dt, the top here, is equal to 0, and the bottom dx dt is not equal to, because you can't have 0 over 0, that's the indeterminate. All right, since dy dt is equal to 3t squared minus 3, this happens when t is equal to 1, or that is when t is equal to plus or minus 1. Right? So I have the corresponding points here where there's a horizontal tangent line, right? Where there's a flat tangent line. If I know when that happens, I can plug positive 1 and 1 into my x and y equations, and I get these 2 points. So these points here, I know they have horizontal tangent lines, so their tangent lines are going to be flat. All right, C has a vertical tangent line, all right, when the bottom, dx dt, which is 2t equals 0, so that is when t is equal to 0, right? So the corresponding point here, if you were to plug 0 into the equations, you would get 0, 0. So there is a vertical, there's going to be a straight tangent line. You can see with my mouse here like this. So the curve is going to come up and probably do this. It's probably going to go whoop, touch it, turn just like that. All right, determine concavity. We look at the second derivative. All right. Here I'm just going to take my first derivative, my dy dx, and just differentiate it again. So I'm going to differentiate it with respect to t, and then I'm just going to slap another dx dt in the bottom. So it's going to look like this, right? This is the derivative, all right, with respect to t of my first derivative. This is another dx dt. And that, just simplifying it, all right, combining here, this fraction here, it just becomes 3t squared plus 1 over 4t cubed. All right, if you want to look at concavity, so concave upward, right, happens when the second derivative is positive. Well, the top will always be positive, so you're only looking at the bottom. So it's concave upward, obviously, when t is greater than 0, right, because the positive number cubed will be positive. And it's concave downward when t is negative, because if you cube a negative number, it'll be negative. All right, so using this information, let's check this out and to sketch the graph. Here are my horizontal tangent lines, right? I said one happened at 1, 2, and one at 1, negative 2. Here's the vertical tangent line, all right? So that what that means is the graph is going to butt up against it. And remember, we said it has to cross each other at 3, 0. So if you were to pick some test points using t, you would see the graph would just look like that. All right, and you can use this information to help you sketch out the rest of it when you go to do your homework. All right, I'm going to pick up the rest of this in a second video below.